Good day, stat students. So today we're going to talk about section 7.1, and we're going to talk about sampling distributions, but for a sample proportion. And so what are proportions? What are percentages again? So let's review that. And so remember, proportions are decimals. Mathematically they're decimals, like 0.32, and percentages 32%, but they tell you exactly the same thing. They tell you part of the total. What part of the group has a certain characteristic? What percentage of the group drives a foreign car? What percentage of the sample drives a foreign car? What percentage of the population, owns a laptop, whatever, or what percentage has a bachelor's degree? So there's a certain characteristic out there, and we want to know what part of the group has that characteristic. That's usually what's going on with proportions. All right. So proportions are from 0 to 1. Can't be negative. Can't be greater than 1. And percentages, it's got to be from 0% to 100%. Can't be negative. Can't be greater than 100%. All right. Let's focus in on a sample proportion. All right. So the symbol for a sample proportion is this P with a hat over the top of it. And yes, we simply call that P hat. We're not a creative group in statistics. All right. And so we need to know this. So from now on, P hat is the sample proportion. All right. Please memorize that. All right. Sample proportion is a statistic. And there's a simple formula to P hat. All right. I'm sure all of us could do this already, but let me give you a little formula here. P hat is simply x over n, where x is the number of successes. Now, where in the world have we heard number of successes before? I think we heard that with the binomial. X is the binomial random variable. All right, and so all we're doing is taking the binomial random variable and dividing through by n, the sample size, and you get a sample proportion. So for example, we sample 20 students and 9 are female. What percentage of the sample is female? Well, what would be a success here? Success would be drawing a student and they are what? They are female. And how many did we get? 9. And so we have 9 over 20 because we looked at 20 students. All right. Oh, there we go. I didn't draw it over, too bad. So we got 9 over 20, which is 0.45 or 45%. Okay. So a lot of times in the problems that we do in Chapter 8 and Chapter 9, we have to calculate P hat. So let's get used to doing that. All right. All right. How about a population proportion or a population percentage? This is a parameter, right? Because this is a measurement that comes from the population. The symbol that we use is lowercase p, and you might be holding your head going, hold on, why are we using p again? Why are we using lowercase p again? We used it with the binomial, right? Well, obviously p had these proportions all related to the binomial, okay? So let me give you an explanation why, and then we'll move on to the sampling distribution of p hat. All right, let me give you a quick little explanation. Recall this type of problem in Chapter 6. 60% of all U.S. adults have corrective lenses. What's the probability of randomly choosing 15 adults and exactly 8 have corrective lenses? Okay, so here, either corrective lenses or don't. A person either has corrective lenses or don't, okay? And so that sounds like success failure type deal, right? Because there's only two possible outcomes. This is binomial. X is binomial, okay? And so we would have said, all right, let's see, we need the probability of success for one trial. We would have said 60%, P is equal to 60%, N is equal to what? 15, and P, probability of X is equal to 8, right? Because we're looking for exactly 8. Now, I don't want you to solve this, okay? That was back in Chapter 6. What I want you to pay attention to is that we said P was equal to 60%. Now, why could we do that? Why did we do that here, all right? And so, regarding the binomial, P is the probability of success for one trial, okay? And I think everybody probably can do that, okay? All right, so I want you to focus in on something else now. Notice here I said 60% of all U.S. adults. All. Total population here, right? So what I want you to do is I want you to kind of pay attention to this next couple of statements here because it ties everything in, all right? That's how probability works. Okay, once you understand the long run probability, now what's the long run probability here? It's this guy. We looked at the entire population. That's kind of unrealistic that we did that. And remember, I told you that sometimes that happens in these problems until we get to about chapter 8. Um, that we looked at all the adults in the U.S. Okay, but assume that we could. All right, there's your long run probability. Okay, and once you know the long run probability, you can take that and apply it to the short term. Okay, for instance, if let's say that you looked at the probability that someone is going to buy a foreign car or a domestic car. Let's say a domestic car, and so the probability that a person in the United States buys a domestic car is maybe 60%. No, let's not use 60%. Let's say 70%. All right, 70%. So that means if we randomly choose one person, what's the probability that he or she is going to buy a domestic car? It's 70%. So once you know what it is in the long term, you can apply it to just one person then, or one trial. Okay, and that's what we did. We learned what it was in the long term, and then we applied it to one trial, which is the binomial. That means that the population proportion P, the long run probability, is the same as the probability of success for one trial regarding the binomial, and that's why we use P as a symbol for both. They're exactly the same thing. All right, you may have to review that little once more, okay, to get a hang of that one, but that's the answer there. All right. So you might be going, hold on, Doug. Hold on. You told me that I thought we used Greek letters as symbols for parameters. That's true, but I did tell you there was one exception. Okay, and this is the exception. Now, does anybody know what P translates into a Greek letter? It's pi. Okay, and doggone it, the mathematicians already use pi. Everybody knows what that should be used for, and so the statisticians couldn't use it. And so we decided, okay, fine, we'll have one exception here. We'll use p, lowercase p, for the parameter and p hat for the statistic. Okay, so that's what's going on. So there's a summary of it. That here's a sample proportion, and that's p hat. It's x over n. By the way, this would also be x over n. The lowercase p. It's just that it would be the number of successes divided by the population size, but you usually don't calculate it. All right. Because we're usually not going to, in reality, look at an entire population. All right. Remember, if we know this number is probably because we're sort of in pretend land, or we're working with a game of chance. Okay. So, because games of chance, you can figure this out a lot of times, but in reality, you would probably just have to make up the number like I just did in the last problem. Okay, that 60% of all U.S. adults have corrective lenses. All right, let's get back to our discussion here, really, our main focus. So here's the question. I asked the students in the class to randomly sample 10 adults, and you record how many of them have corrective lenses. Okay, so glasses or contacts. Then you calculate the proportion or percentage of the 10 adults that have some sort of corrective lenses. All right. So student number 1 finds 6 adults with corrective lenses. And so remember, finding a person with corrective lenses, that's a success here. Okay, doesn't sound very much like a success, but it is here. All right, so that means X is 6. And how many adults did we take a look at? 10, right? So we have 6 over 10, or 0.6 or 60%. Okay, and that was for person number 1. Okay, but person number 2 is going to probably look at 10 different adults, and do you think it would be okay that he or she found just 4 versus the 6 over here? Yeah, because it was 10 different adults. Okay, and so maybe her p hat, so for the second person, turned out to be what? 0.4 or 40%. Okay, so what did we just learn about a sample proportion, p hat? Well, what we just learned is that p hat varies from sample to sample, just like every other statistic, just like x bar did. P hat, sample proportion, varies from sample to sample. All right, so the first person had 60%, the next person had 40%, maybe the next person had 40%. That's okay. So these p hats could repeat itself, okay, and that's going to happen when you only look at 10 people, certainly. And so our made up 36 people, maybe the 36th person found 50%. That's perfectly fine. So notice p hat is varying from person to person, okay? And let's combine all the p hats together into a histogram. And once you do that, what are we creating again? Remember when we put all those statistics of a certain sample size into a histogram? We're calling that a sampling distribution. And here it's the sampling distribution of p hat. Okay. So we always have to. Oh, hold on. Let's see. For a sampling distribution of p hat, we're going to use this symbol right here. That shouldn't be surprising because we used x bar with the parentheses for the sampling distribution of x bar. So sampling distribution of p hat, we're going to use that symbol right there. Okay. And we always have to learn three things about a sampling distribution. We always have to learn about a mean, a standard deviation, and a probability distribution. All right. So let's investigate those three things with regards to p hat, the sampling distribution of p hat. First thing, the mean of the sampling distribution of p hat always seems to give students some problems. Okay, and so let me develop this a little bit. All right, here's our made-up data again. Okay, and let's just focus in on these two people right here, this person and this person right here. Let's say that we average these two people, right? The mean, okay, of p what we're talking about is the average of all the p hats, right? And so if you averaged 60% and 40%, what are you going to get? You're going to get 50%. Okay? You're going to get a percentage. See, I think what happens is that a lot of students, they go, hold on, means are usually things like 3 or 8 or 6.2 or 50 or whatever. They're not percentages, or they're not proportions. They're okay. But in this situation, if you average a bunch of percentages, okay, so if you average a bunch of percentage, the mean of them is going to be what? It's going to be another percentage, okay? And so don't be surprised that once we average all the possible p hats, now not just the 36, but from every possible sample, all right, of a certain sample size, if we average all of them, it's going to come back as a percentage. So don't be surprised over that. Okay? Don't be surprised over that. So what we find out is that the mean of the sampling distribution in value is equal to the population proportion p. It's a percentage. Now I'm not saying to use this as a symbol for the mean of the sampling distribution of p hat. That would be incorrect. What we're saying is that in value, all right, the mean of the sampling distribution of p hat is going to be some sort of percentage, and what is that percentage going to be? It's going to be lowercase p. It's going to be the population proportion. That's it. Okay, hopefully that makes sense. 2, the standard deviation. So here's the standard deviations calculation. It's very much related to the binomial. Okay, if anybody wants to know how those two are exactly related, let me know, and we can do a WebEx and I can show you really quick. Okay, meaning how to go from the standard deviation of the binomial to this. It's actually fairly simple, but it's beyond the scope of this course. All right, and then 3, which population distribution does the sampling distribution of p hat take on? All right, and there's just one rule here. Remember, there's 2 rules with regards to the sampling distribution of x bar. Well, here there's just one. The one rule is this: if both n times p is greater than or equal to 15, and n times 1 minus p is greater than or equal to 15, so you need both. So you need this to be true, and you need this to be true. Okay, so if this is true and that is true, then the central limit theorem applies. Okay, and what does that mean? Is that the sampling distribution of p hat is approximately normal. Remember, I told you that the central limit theorem applies to more than just the sampling distribution of x bar. Okay, here it also applies to the sampling distribution of p hat. Okay, and so if this applies, This applies. The CLT is good. Okay. And the sampling distribution of p hat is approximately normal. You might ask, hold on, if it's not greater than or equal to 15, both of these things, what is it? It's binomial. Actually, it's binomial no matter what. It's just that what happens here is that once we get to chapter 8, what's called confidence intervals, it's really hard to use the binomial. And so we would like the central limit theorem to apply in those problems because it's so much easier to work with. Okay, and so let me say this, is that when you work your problems out in homework, the central limit theorem will apply, so we can use the normal approximation. Okay, when you take your test, this will apply. Okay, and so let's just say that you won't see a problem where n times p is less than 15 or n times 1 minus p is less than 15. Okay, the central limit theorem will apply to the problems that you're doing. Okay, so that's a good thing. All right, but we should memorize this. Okay, we should memorize these conditions of when the central limit theorem applies to the sampling distribution of p hat. All right, so I described it in words. Let's go over to StatCrunch, and there we go. So let's run some simulations. Yeah, there we go. Okay, so here we're going to come down to binary, and so we get to make up a value for p. Let's say we put in 0.4. All right, and so what that means is that so the way StatCrunch is representing successes, it's representing successes with a 1 and a failure with a 0. And so notice here, if you go from 0.4 over, it's saying in the population you have 40 successes, and if you have 40% that are successes, that means 60% are failures, and that's why 0 is up to 60%. So zeros are represented by failures, successes by 1s. And so here's the population distribution. Here's p of 0.4, and here's our sample size of 2. Okay, and so we go ahead and sample once, and so it randomly picked 2 people from the population. The computer picked 1 failure, 1 success. Okay, and so notice that you have 1 success, 1 over a total of what? 2 people. So 1 over 2 is 50% or 0.5. So the p hat for that particular person would have been 0.5. All right, excuse me, not for that person. That was my mistake in saying that. For that sample, because we sampled 2 people. My mistake. It wasn't just 1 person, it was 2 people. Okay, so now we'll have the computer go ahead and we'll sample again. All right, so this time the computer picked randomly 2 people with a failure. Okay, and so let's see, 0 successes over 2 turns into 0. So that's why I put the p hat here for that particular sample. So it's gathering up all the p hats into one spot. All right, what is it creating down here? The sampling distribution of p hat. So we do it again. We do it again. Okay, and so on and so forth. I'm actually waiting. There we go. That's what I was waiting for. Is that now we had 2 successes. So now we have 2 successes over a sample size of 2, and that would have produced a 1 or 100%. And so, excuse me, these are the only possibilities with regards to the p hat. And let's see what the sampling distribution turns out to be in this situation. So I just ran about 40,000 samples here, okay? And notice here it's trying to look sort of like a bell-shaped curve, but it can't do it yet. Why? Because the central limit theorem isn't applying yet. Let's think about this. P is equal to 0.4. If you take 2 times 0.4, is that greater than or equal to 15? Heck no. That's too small. Okay, so we already know that the sampling distribution of p hat should not be normal because the central limit theorem is not applying yet. Okay, so that's why this isn't turning normal. All right, so let's let's investigate something that would turn normal, and then we'll look at the other things. Let's say that we jack the sample size up quite a bit. Let's say up to 100. Okay, so that means that now the computer is going to randomly choose 100 things. I shouldn't say 100 things, but probably more like 100 people. Okay, and this time the p hat turned out to be 0.39. Okay, so we do this a whole bunch of times, and look at the beautiful shape that it turns into, the sampling distribution of p hat. Okay, so I just ran 50,000 samples. Okay, and let's see. So let's make sure that the central limit theorem would apply here. So if you don't have your calculator, pause the video, go get your calculator, and come back. So let's assume that you got your calculator. Okay, and let's see if what would be 100 n times p, n times p. So that would be 100 times 0.4. That would be 40. Is that greater than or equal to 15? Yep. Okay, so we got the one side. Then we have to multiply n times 1 minus p. So 100 times, let's see, 1 minus p, 1 minus p, 1 minus 0.4 is 0.6, right? So 100 times 0.6 is 60. Is that greater than or equal to 15? Yes. So both of those are true. Both of them are greater than or equal to 15. So the central limit theorem applies. And so what should the sampling distribution of p hat look like? It should look like this, a nice bell-shaped curve that is very much normal looking, approximately normal anyways. Okay? So that's one. And then two, take a look at the average of all of these p hats. It turned out to be 0.4, right? That's what it should have turned out to be. So this is truly the average of the 50,001 samples for all those p hats. The average turned out to be 0.4, and what should it be? 0.4. So this graph here should be centered at 0.4, okay? The population portion p. And then, if you got your calculator out, let's do a quick little calculation. Let's do the square root. So we're going to figure out the square root of p times 1 minus p over n. So remember, p is 0.4. 1 minus p, let's see, 1 minus 0.4 is 0.6. And we'll divide that by 100. So when I put that in my calculator, theoretically I came up with 0.0489. So it's kind of like 0.049. And so notice here this turned out to be 0.049 also, okay, when she rounded to 3 decimal places. And so this is what pretty much it theoretically should have come out to, okay. So there's your simulations, okay. Now if you haven't gotten it yet, okay, that this is the sampling distribution of p hat and it's turning into a nice bell-shaped curve with these characteristics, let's do a problem. Let's go back to our presentation. Let's go back to our slides here, okay, and let's pick it up from here. So here's a problem. The proportion of all U.S. females between the ages of 16 and 24 that routinely plays video games is 0.2. Suppose we repeatedly sample 400 U.S. males of this age randomly, and that means we're going to investigate the sampling distribution of p hat because we're doing this over and over and over again. Okay. So what did we just find out? Let's see. The proportion of all U.S. females. What is that? That sounds like lowercase p, and that in value is what? Turns out to be 0.2. Okay. Oh, I skipped over this. I'm sorry. I shouldn't have. So what's a success here? It's finding a female that plays a video game routinely. Sorry. And what proportion of the population routinely plays video games? And with regards to this age group, it's 0.2. So 20% of the female population in this age group routinely plays video games. What's our sample size? Our sample size looks like it's what? 400, because suppose we repeatedly sample 400. So our sample size 400. Okay? So what is the probability distribution of p hat? So we have to make sure that what? The central limit theorem applies. So we have to verify it. So we have to take n is 400, times p of 0.2, that's 80. Is that greater than or equal to 15? Yep, check mark. Let's figure out the other side. N times 1 minus p, let's see, that's 400 times 1 minus p, that's 320, that's greater than or equal to 15. Yeah, check mark. We got that side, so does the central limit theorem apply? Absolutely. The sample size is large enough for all this to happen. So since the central limit theorem applies, and that means the sampling distribution of p hat is what? Approximately normal. It should be nice and bell-shaped like we just saw in StatCrunch. Okay? All right, good. Let's move on to the next thing. What should we look at? The mean, right? We found out that the mean of the sampling distribution of p hat in value should be the population portion p. What's the population portion p? 0.2. So where should that bell-shaped curve be centered at? It should be centered at 0.2. Okay? That's all. All right. Sound good? Move on to standard deviation. So, let's see here. I bet you that was one slide too early. All right. So the standard deviation of sampling distribution of p hat is this guy right here. Okay. Let's go ahead and calculate it. So if you still got your calculator out, go ahead and calculate this out. So we got 0.2. You know, a lot of times students make this too difficult. I would do this calculation ahead of time. Everybody can pretty much do that one ahead of time. 1 minus 0.2. What is 1 minus 0.2? It's 0.8, right? And so maybe you do this calculation ahead of time instead of trying to put all these parentheses in your calculator. So put in your calculator, what's 1 minus 0.2? It's 0.8, right? So put in your calculator the square root of 0.2 times 0.8 and divide that by 400. Close your parentheses. What do you get? You get 0.02. Okay, 0.02. Okay, for your standard deviation. All right. So we got our three things. What should we do probably now? We should go ahead and draw a graph. Okay, well, let's draw a graph. Let me remind you of the things here of what we just learned. P hat is approximately normal, and it should be centered at 0.2, and the standard deviation should be 0.02. So I had the computer draw it for us. So I had the computer draw a normal looking curve that's bell-shaped, right? It's centered at 0.2. And notice the standard deviation. We go out 0.02 units here, so we're at 0.22, 0.24, 0.26, right? And then we go out 0.02 this way, and so on and so forth, right? Okay, so let's go out one standard deviation this way. Let's go out one standard deviation that way. So if we do that, what percentage of all samples will produce then a p hat between 18% and 22%? And hopefully you say, oh, that's the empirical rule, right? So about 68% of all samples with an n of 400, okay, will produce a sample proportion between 0.18 and 0.22, between 18% and 22%. Go out one more standard deviation. We're going to be at 16% and 24%. So about 95% of all samples with a sample size of 400 will produce a p hat between those 2 points. Okay, go out one more standard deviation. So we're all the way at pretty much at the end of the curve. Now, is there more data past there? Yeah. Technically, this goes further out this way. Okay, but there's so little data out there, right? So about 99.7% of all the samples will produce something between those 2 points. And that was the whole purpose of this, to see how p hat is going to be limited and what percentage are going to be right here in the middle, one standard deviation away, two standard deviations away, three standard deviations away, and so on and so forth. All right. Now, if you didn't quite get it, let me give you a real life example. Okay. Here's the second and last example with regards. Okay. So, let's go back to the 2012 presidential election. That would have been the re-election of President Obama. Okay, let's take a look at that. Now, he ran against Romney. Okay, and let's take a look here. I looked it up. one a couple of websites told me this. It says the proportion of all voters that voted for President Obama in his reelection was 51.2%. Okay, so this is all the voters, right? And so what is this? See, this is one of the few times in real life that we can actually figure out what the population proportion P actually is, because we can go back to the election, see how many people voted, see how many people voted for President Obama or whoever for that matter. Okay, and so it's one of the few times that we can actually see this. All right, and so P in the problem is what? 51.2%. Okay, now what do we always do before the election? We're always doing these political polls, and we're seeing, we're getting a gauge of who people are going to vote for. Okay, so these news organizations does this, and we see it on the news and social media and the internet and so on and so forth, right? So suppose before the election, a news organization does a political poll of 1,000 potential voters, and that's pretty much what a news organization will do. They will look at about 1,000 people. Okay, assume this was done repeatedly. Okay, so here X, well, what would be a success here? A success would be finding a person who voted for President Obama in his reelection. Okay, and we found out that P is equal to 51.2% and N is equal to 1,000. Seem reasonable so far? So what is the probability distribution of P hat? So we have to make sure that this central limit theorem applies. So we got to do our calculations, and if you put your calculations into the calculator, you'll see that both of these apply. N times P is equal to 512. That's greater than or equal to 15. N times 1 minus P is 488. That's greater than or equal to 15. Since both of them apply, the central limit theorem applies, and the sampling distribution of P hat is what? Approximately normal. Okay? Sound good so far? Go to means. See what the mean of the sampling distribution of P hat is. In value, it is equal to 51.2, or if you want, 0.512. Okay, so that's where it's going to be centered, that graph. How about the standard deviation? Now the standard deviation, a little bit more complex. Again, if you want to do this, you can do this in your calculator, 1 minus 0.5122. If you do that, I think you're going to get 0.488. And so you can take 0.512 times 0.488 divided by 1,000. I think this is what you're going to get for the standard deviation. So now, this is real data, okay? The last set of data I made up, and I made it, all this stuff come out real nice as far as the standard deviation goes, but this is real data, okay? And so since it's real data, it gets a little messier, if you will. But the good thing is that we can put all this stuff in the computer, and the computer can draw the graph for us real nicely, okay? So here's what we just found, is that P hat is approximately normal. It should be centered at 0.512, and there's the standard deviation. So let's see what the computer drew for us. All right, so let's see here. Here's the sampling distribution of P hat. It's nice and normal looking, so it's going to be bell-shaped. Where is it centered at? 0.512. Okay, and then I had the computer, I put in the computer 0.0158 for the standard deviation, and it took it out to 3 decimal places. Okay, so there's 1 standard deviation, there's 2 standard deviations, there's 3 standard deviations, and so on and so forth, and 1 standard deviation, but in the negative direction, and so on. Okay, so we draw a line here, we draw a line here. Okay, so what percentage of the data is going to be, what percentage of all samples will produce a P hat between those two values? And hopefully you say, well, okay, about 68% of all samples, the size of 1,000, will produce a P hat between these two values here. Sound redundant? Yeah, because hopefully you're getting it by now. Okay, and so if we drew a line here, we drew a line here. Okay, what percentage of all the samples will produce a P hat between those 2 points? 95%, right? And then we draw this line here, right? Draw a line here. Technically, this graph is going further out. So what percentage of the data is between those 2 points? 99.7%. So 99.7% of all the samples will produce a P hat between those 2 points. Okay. So um, hopefully by putting it into a problem that is real, okay, sort of brings it to life a little bit. So here I kind of made it not very clear that it was always sitting there, but down here is a news article on the internet about it was 2 days before the actual election, and they were doing political polls, and they basically said, boy, we can't tell the difference between these guys. Basically both candidates are getting about 48% in our poll. Okay, and so let's see, 48%, 0.48 is right here. Okay, so it's a little lower than what actually President Obama got. Okay, but is that all that far off? It's what, two standard deviations. We expect things to be within one or two standard deviations of the middle of the sampling distributions. Okay, when we go ahead and sample, and so I think that was something reasonable to get for that particular sample of 0.48. What wouldn't be something reasonable if we start getting something like what, like 2.5 standard deviations out? So if we took a sample and we got something that was out here, okay, a p hat that was out here, okay, that would be sort of unreasonable or unlucky, um, or maybe out here, maybe that, okay. So we got something way too high or way too low, more than, you know 2.5 standard deviations away. Well, that particular poll, it was 2 standard deviations away, and it was a little low, but that was okay because of the randomness of the whole thing. Okay, so this is the reason why that when you see these political polls, you won't see one week the candidate get 33%, and then the next week or another poll, he or she's going to get 63%. You know, that's why you don't see these wild swings in these political polls. That's why they're so close from week to week. Okay, why? Because it's all bound by the mathematics behind a sampling distribution for p hat. It's right here. Okay. So, anyways, hopefully that brings it to life a little bit. Okay. And so that ends our presentation for sampling distributions of p hat. All right. Have a good day. Thank you.